Okay, so this is page 26, and we're going to do this page here, and then also, guys, we are going to do page 28, but then we'll stop there. I think lesson 12 is going to be a little too long, and this one is pretty short, so let's just put the beginning of lesson 12 on this lesson. They're very closely related. Okay, so this is about understanding horizontal asymptotes through limits. Okay, so if the limit as x approaches infinity of f of x gives you a, that's going to happen if and only if y equals a is a horizontal asymptote for the graph of f of x. Okay, so that is why if you look at your decision map, there's a branch here that where x is approaching infinity. So we're seeing this part for the first time. We've been only doing like this stuff. All right, so if you're looking at a limit and x is approaching infinity, then you've got to do like, this stuff down here. But we'll do that. We're going to talk about growth competition next lesson. But if the limit as x approaches infinity, if you end up just getting a number, that is going to indicate a horizontal asymptote. Okay, so I just kind of said the same thing there. Okay, so you are given a horizontal asymptote using either a limit or a sketch. Fill in the missing representation. Okay, so the limit as x approaches infinity of f of x equals 5. Okay, so what this means is as there is no wall. Okay, x is not approaching a wall. X is moving further and further and further right without end. Okay, so if you're looking at like a sequence of numbers, like x is 10, then it's 100, then it's 1,000, then it's 10,000. It just keeps going. X just keeps getting huge. And they're telling us that as that happens, the y values, the graph, is leveling off at 5. Okay, we're leveling off at 5. So even though the x's aren't approaching a wall, we are still going to level off. We're still going to hit like a certain level. So anyway, let's do just the x-axis. And then we'll put in this horizontal level, and we'll label it y equals 5. Now, guys, you have a lot of options, okay? As long as, like at the end of the graph, I am looking something like that, or I could be coming from the top as well. As long as it's something like this, like leveling off at that line. And again, the graph could be coming from the top as well. It doesn't matter what the rest of the graph looks like, okay? So I'll just make it very simple and just have it something like that, okay? But you could be doing a lot of things. There's a lot of correct answers here, and they don't have to be. They could even cross the level, like they could even cross the line. Okay, so I'll talk about that in class. Or show more examples. All right, so then we've got the limit as x is approaching negative infinity of f of x equals 3. So again, we're not hitting a wall, but instead of moving right without end, we're moving left. The x's are moving left, left, left without end. And as time goes on, the graph is leveling off at the y value 3. All right, next. All right, y equals 3. All right, and now we could be coming from below again. I guess I'll just come from below again. And as long as like we're like leveling off, then the shape of the graph doesn't matter. All right, something like that. Okay, now down here we're given the graph and we need to state the limit. So first, all right, so here's the line. All right, so we know that the limit is going to be 2. But is x approaching positive or negative infinity in order to level off at that value? And then so just look at the graph at the ends, and it is going to be positive infinity. So the limit as x approaches positive infinity of f of x equals 2. And notice in this example, I even crossed the horizontal asymptote. Horizontal asymptotes can be crossed. And then over here, so this time it doesn't look like we're leveling off as x's go right, but yeah, as x's go further and further left, we're leveling off at -7. So the limit as x approaches negative infinity of f of x equals -7. Okay, now let's turn to page 28 and take a look here. So we're just going to do this page. So limits at infinity. First, we'll look at the limit of a constant function, and then we'll do examples of limits at infinity. Okay, so most of the examples, like the real heavy-duty ones, we're going to save for the next video. Okay, and guys, I think you've already maybe noticed this, but if you're doing the limit of a constant, it doesn't matter whether x is approaching a wall, what side it's approaching from, if x is approaching infinity, it's just that constant. That constant is the answer. So the graph itself is a horizontal level. So that's just 9. The limit as x approaches 1 from the left of 9 is 9. The limit as x approaches 4 from both sides of 9 is 9. The limit as x approaches infinity of 9 is 9. The graph is just a horizontal line. So no matter what x is doing, the y's are always 9. Okay, now before we look at these examples together, I just want to point out that, okay, let me say this. All right, so T is going to mean top, B is going to mean bottom, okay, and so doing these limits, all of these 4 limits are what are called limits at infinity. So we're doing a limit, x is approaching infinity. We've got to use this thing called growth competition, or I call it that. It's not called that. Maybe some other people do, but I'm calling it growth competition. So you're asking yourself which terms are outgrowing others. And specifically, if you've just got like a single fraction with a single term on top, single term on the bottom, the limit is going to be 0 if the bottom outgrows the top, and it's going to be infinity if the top outgrows the bottom. Okay, so if you want to pause and write that down, you can. But okay, so the limit as x approaches infinity of -1 over x squared. Okay, so think about what's happening to the denominator here as x approaches infinity. It's getting very big. 10 squared, 100 squared, 1,000 squared, 10,000 squared. So this denominator is just getting huge. And if you have your calculator with you, you could divide -1 by some huge number. You're going to get a very small number. So this is a case where the bottom outgrows the top. The top is just staying -1. So if the bottom is outgrowing the top, guys, the graph is going to level off at 0 as x approaches infinity. Okay, so here's another case. The limit as x approaches infinity of 8 over 5x cubed. This is the same situation. The top is just 8, and then the bottom is just getting bigger and bigger and bigger as time goes on. So same situation. So eventually this graph is going to level off at 0. The entire fraction is shrinking, shrinking, shrinking if the bottom is growing. Okay, now here is a case, the limit as x approaches infinity of -7x over 2. Okay, now the bottom is staying 2, and in the top, think of plugging in bigger and bigger numbers. 10, 100, 1,000, 10,000, a million, a billion. The top is going to get huge and the bottom is just like staying as it is. So we've got the top outgrowing the bottom. So this is going to be an infinity. If the top just keeps growing and growing, that means the whole fraction is growing. All right, but just be careful here, guys. When you're plugging in bigger and bigger numbers, they are bigger and bigger. The outcome is negative. So we're just getting bigger and bigger negatives because of this negative here. So the answer would be negative infinity. Okay. And then this is another case, same idea, where well, we haven't even looked at it yet, but the limit as x approaches negative infinity of this fraction here. The bottom is just staying 6. The top is growing and growing. But let's think about that, because x is approaching negative infinity. So imagine plugging in bigger and bigger negative numbers, negative 10, negative 100, negative 1,000, negative 1,000,000. So the top is getting huge, but it's also being squared. So the entire outcome is going to be a really huge positive numbers. So positive infinity. Okay, almost done, guys. Now down here, if you're doing the limited infinity, a limited infinity of e to the x or e to the negative x, it helps to know their graphs. And we did spend some time on them last year, so hopefully this will be familiar. All right, so we need to know these 3 graphs. Okay, so this one, it goes through 1 on the y-axis, and it looks like this. This is y equals e to the x. Okay, it's an exponential function. It grows exponentially. Now, let's do e to the negative x. That is still going to go through 1 on the y-axis, but it's going to be like that. E to the negative x, okay? And then finally, we won't look at this one till tomorrow, but the natural log graph goes through 1 on the x-axis, and it goes like, that's a vertical asymptote, and it goes like that. Okay, so it does keep growing as x's move right, but not exponentially. Exponential growth would look right like that. Okay, so let's use these graphs, or these 2 anyway, to evaluate these limits. Okay, the limit as x approaches infinity of e to the x. Okay, so as we move further right on the graph, the y's are just shooting up without end to positive infinity. Okay, so you could use the graph, or you could even think it through like, I'm plugging in 10, so e to the 10th, e to the 100th, e to the 1,000th. The number just keeps getting bigger. Okay, the limit as x approaches negative infinity of the same graph. So approaching negative infinity means you start on the graph and then you just move left, further and further and further. And as we move left, further and further and further, the y values are leveling off at 0. Okay, so that answer is 0. Now this one here, the limit as x approaches infinity of e to the negative x. Okay, so this time we're using this graph. So x is approaching infinity, so I start like here on the graph, and then I'm just moving further and further right. And as I do that, the y values in this case are leveling off at 0. So the y values are shrinking close to 0. Okay, and then same graph, the limit as x approaches negative infinity of e to the negative x. So x is approaching negative infinity, so I'm on the graph and moving left without end, and the y's are just shooting way, way up. Okay, infinity. There it is, guys.